Okay, so this is beginning of week 6, and before we start, let me point out where we are in our textbook. So if you're look at the textbook, we don't actually go through entire contents of the textbook, but basically we covered all of chapter 1, okay? And from chapter 2, we're talking about a second order linear ordinary differential equation. So that's what we are going to do from this week. And basically the first early sections of chapter 2 covers the method of finding solutions of second order ODE. And in the end of chapter 2, they talk about some modeling of spring motion and possibly some RLC circuit model. So, yeah, and then it goes to another material. So read through chapter 2 very carefully because this week we're going to cover in almost all material of chapter 2. The reason why we can do that is we covered some of the material in chapter 2 in previous week, such as existence of solutions and the principle of superpositions and so on. And the homework is up right now. So if you're looking at homework, most of questions are finding solutions using the method that we are going to cover this week. Okay, so we're going to learn four main methods. One of the method is the reduction of order. But before we start, let's review such four methods. So in order to find the solution of linear ordinary differential equation, so in this chapter we are going to talk only about second order linear differential equation, okay? Second order linear differential equation. We first find its complementary solution and then a particular solution. So complementary solution is the solution of differential equation where there's no non-homogeneous term. And then particular solution is a solution, not a general solution, without any constants, satisfying the entire solution. So in the homogeneous case, first case, if we know a solution, that's the one condition here, we can use the method of reduction. Let me highlight here. So the method of reduction here in order to find another one. So when you solve second order linear differential equation, you need two fundamental solutions. So remember that the fundamental solution is the set of solutions which are linearly independent, and the method of reduction assumes that you know one of the solution, okay, and the method tells you what's the next solution, okay. So that's the one method. And if you have a linear ordinary differential equation with constant coefficient, so this type of differential equation have a solution using the characteristic equation. So the second method is using the characteristic equation, okay? If there is a constant coefficient in your differential equation and the differential equation is homogeneous. And a little bit of generalization is that if you have an ordinary differential equation with a coefficient, not a constant, but with a consistent form of the following, such that the coefficient of y double prime is alpha 2, which is constant, times x squared. So entire alpha 2x squared is a coefficient of y double prime. And for y prime, you have alpha 1x, okay? And for y, since this is zero order derivative, you have x to the power of 0, so you just have alpha 0 as a constant. So if this form, the differential equation of this form is called the Euler equation, okay? So we're going to learn how to solve the solution of Euler equation. And for non-homogeneous case, there are two methods of finding a particular solution. So when you find a solution of non-homogeneous case by principle of superposition, you first find a complementary solution and a particular solution. The previous case is finding a complementary solution, and this case, non-homogeneous case, is finding a particular solution. And one method is method of undetermined coefficient. If the non-homogeneous term f of x is given fairly simple functions such as polynomial or sine or exponential functions. And another method is method of variation of parameter using it, and this method uses the fundamental solutions from the complementary solutions to find a particular solution. So we're going to learn that in this week. Okay, let's first talk about reduction of order. So assumption is that we have this form of differential equation. So this form of differential equation. Be careful that there is 1 on the coefficient of y double prime. So if you have if you are given with a differential equation of some coefficient on y double prime which is not 1, then you have to divide both sides so that the highest order derivative has always the coefficient 1. Okay, so px and qx are given when the coefficient of y double prime is 1. And we assume that y1 is a solution of this differential equation. Then reduction of order says that there is another solution which is another fundamental solution, which means that it is linearly independent to y1 given by this formula. So you can just memorize formula, but I do not recommend just memorizing it because we're going to see how this formula derives. So think about this formula carefully. So it says y2 is y1x, the given solution, times some indefinite integral. So indefinite integral gives you a constant after multiplying, after computation. But if you have plus c, then it basically means that y2 is constant times of y1 plus some y1 times some other function. So when you express your complementary solution, you will have a constant times of y1. So you don't need to put the constant after you compute this indefinite integral. I will explain what that means. And also, there is a indefinite integral sign on the exponent of e on the numerator, and also you don't have to put the plus c here. So, okay, let me derive this formula first, and then let's look at the example. So, this is our setup: y double prime plus pxy prime plus qxy equals to 0. So note that this is homogeneous equation, homogeneous differential equation. And let's say we know that y1 is solution. So let's say y2 is another solution, and I can express my y2 as y1 times u. So u is unknown yet, but any function y2 can be obtained by multiplying some other function to y1. So I'm just assuming that y2 is multiple of y1 with some function u. So u is a function, not a constant function. And we assume that this y2 is solution to this differential equation. So let's plug into the equation. So first derivative y2 prime is y1 prime u plus y1 u prime. And second order derivative is y1 double prime u plus 2 times y1 prime u prime and y1 u double prime. So plug into the equation here, we have y1 double prime u, 2y1 prime u prime, and y1 u double prime, so that's y double prime, and plus px of y prime here, y1 prime u, y1 u prime, and qxy, y1u. So I want this to be equals to 0 because that's the assumption that y2 is a solution to this differential equation. Let's combine some terms here. You have a term which contains u. So here's u, and here's u, and here's u. Not u prime or u double prime. So if you combine u and putting all the other terms together, you have y1 double prime, px y1 prime, and qxy. And the rest of the terms, it looks like 2y1 prime u prime plus y1 u double prime plus px y1 u prime, and that must be equals to 0. But we already know that y1 is a solution to this differential equation, and this term is nothing but the left hand side with y replaced with y1. So this is always 0. So this part is 0. So we want this part to be 0. We only want this part to be 0. So note that u is not determined yet. So our goal is to find u satisfying this equation. So let's combine u prime here. You have, okay, so let's put the y1 u double prime first, and then take the u prime part to the right hand side. What we get is minus 2y1 prime plus px y1 u prime, right? And you see, it almost seems like it's the separation of variable if you replace t with u prime. So then t prime is u double prime. So I can rewrite this equation as sending y1 to the right hand side. This is t prime divided by t equals to minus of 2y1 prime y plus px, right? So I take the u prime to the left hand side, so that's where I get the denominator t, and y1 to the right hand side, here y1, and this y1 cancels out, and this one becomes the fraction. Now t prime is nothing but dt over dx, so I can rewrite this into dt dx. Okay, and then take the integral. So on the left hand side I get ln t. So So I don't want to put the absolute value sign because I'm just taking indefinite integral. And also I don't want to put the constant plus c because well, okay, so suppose that I put some constant c, you see what happens here. So that, okay, so put this constant c right on the left hand side and see why we don't really need constant c later. And how about this part? So the first integrand becomes minus 2 times ln y1, and px, integral of px is unknown, so let's leave it as the integral sign, so px dx. Yeah, so that's it. And ln t, let me write it above here, ln t is equals to, so let's put c on the right hand side. So it becomes ln of y1 square, 1 over y1 square, and minus of integral px dx. And let's express in terms of, let's take this log out. So we get t equals to e to the ln 1 over y1 square minus of px dx. Okay, so here's c, okay. And then this becomes y1 square, and this becomes simply e to the minus px dx. Now, what happens to e to the negative c? So that becomes separated to e to the negative c. So c is any constant, c is any real number. So e to the negative c becomes just positive random number, right? So I can replace this as some a, okay? So let's say this is a times y1 square e to the negative px dx. And that's not it, because t is u prime. What we want is what's u. So u is the integral antiderivative of t. So we have to integrate this thing. So a times y1 square e px dx. Now you see, we actually didn't we didn't need to put c in the beginning, because what happens when I put c, a constant c, is that I get the constant a here, but what happens at the end is I just want the fundamental solution. I just want a particular solution that serves as a fundamental solution. So suppose that I get this formula as u, then what I get is a times y1 integral y1 square e to the e minus integral px dx and dx. I'm sorry that there is dx missing. Now, and then what I'm going to do with y2 is just put a linear combination with y1 and y2 and express my complementary solution, or the solution, general solution to this second order differential equation with c1y1, c2y2. Now there c1, c2 appears as a arbitrary constant, and also there is another arbitrary constant a. I don't need a arbitrary constant multiplied together to represent a arbitrary constant. I just need one. So you don't need to put a here, because there is going to be arbitrary constant multiplied to y2. So I just need a particular solution y2. So I don't need a here. Or you can just assume that c is equals to 0. So I don't have to put c. Here. No, nowhere here. Okay. So here's the formula. y2 is given by this formula. So what happens after I put integral, after I compute the integral, what happens if I put the plus c at here? Then it simply makes y2 is this function plus some constant times of y1. And I put the complementary solution. There is a constant times y1 appears in the formula. There is a duplicate, there is an addendum on the y2 part. So I don't need to put the constant term in the indefinite integral right here. So this is just this is formula that you can just compute without worry about the constant c. Let's look at some example. So when you solve questions, you can just simply apply the formula. But you have to understand why we are doing that. Okay, so first one, you can do the second one by yourself. So you have y1, the first solution, e to the 2x, and find the next solution to y double prime minus 4y prime plus 4y. Okay, and let's do the both. Okay, there two examples have different nature, so let's do the both. So the second solution is y1. So y1 is e to the 2x integral of y1 square e to the 4x and integral of e to the minus px. Px is minus 4 dx. So this is e to the 2x times integral. So this is plus 4x. So e to the 4x, e to the 4x dx. So this is 1. So integral of 1 is x. So therefore, x times e to the 2x is our second fundamental solution. So I didn't put the constant c anywhere in the indefinite integral because of this argument. So this is the second solution. You can check why this is second solution. Simply plug into the differential equation. And let's look at the second one. So now, this is what I want to emphasize. So we have x, 1 minus x squared as a coefficient of y double prime plus 2x y prime plus, now you can just assume that the coefficient of y is 0. That's why we don't have y in the equation. Now, this is not 1, so you have to multiply 1 minus x squared on both sides. So you get y double prime plus 1 minus x squared, 2x y prime plus, well, 0 equals to 0. So this is our px, 2x over 1 minus x squared. So y2 is, we know that y1 is 1, so 1 times of 1 squared and e to the negative of 2x 1 minus x squared dx. So just delete ones here. We have e to the negative of, let's do this without putting any. So when you take an integral, this is ln 1 minus x squared dx, right? So if you take the derivative of ln 1 minus x squared, you get minus 2x over 1 minus x squared. So e and ln cancels out. So I don't want to put the absolute value sign because I don't have to check the range of x because this is indefinite integral. So you don't have to worry about the absolute value signs. So this is 1 minus x squared dx. And then this is simple polynomial. We have x minus 1 over 3x cubed. So I don't put the constant c because that's already appears as a first solution. So this is our second solution. Okay, so the question asks to find the general solution. So for the first example, the general solution is y equals to c1 times y1, which is e to the 2x, and c2 times e to the 2x. And for this question, the general solution is y equals to c1 times 1. Okay, so simply c1 plus c2 times x minus 1 over 3x cubed. So this is the general solution. Any questions? No questions? Is it easy? It should not be hard because that's the only beginning. We even passed the half of our semester. Okay, let's look at the next method. So characteristic polynomial. I think some of the students who done the homework 1 found some of the materials on characteristic polynomial on the problem that I asked to find, check the given formula is the solution of spring motion. And this is the method actually find the solution. So our setup is we have second order linear differential equation with constant coefficient. So this is a slightly different setup from the reduction of order because we need a constant coefficient, and the coefficient of y double prime does not have to be 1, and unlike the reduction of order, we don't have a given solution. We start from differential equation. Okay. Now we replace the y double prime with lambda square, and y prime with lambda, and y with 1. Okay. Then this equation is called a characteristic polynomial. Okay. We simply call this as a characteristic polynomial of differential equation. So that's why we need a constant coefficient for every differentials of y in the equation. Now the theorem, so after I explain the theorem, let me explain why this theorem works. Let's say lambda 1, lambda 2 be two roots of characteristic polynomial, characteristic equations. And if lambda 1, lambda 2 are distinct real numbers, real roots, then e to the lambda 1x and e to the lambda 2x are fundamental solutions of the given differential equation. So that's the one case, because when you have a quadratic equation, you have three cases. The first case is that you have two distinct real roots, and second case is you have a double roots. Okay, they have the same lambda 1 and lambda 2. In that case, e to the lambda x is one solution, and another solution is x times e to the lambda x. You just multiply x. And third case is that you could have a complex root, and complex root always comes with a pair. One is a conjugate of other. The conjugate means that if you express your complex number as a real part plus I times the imaginary part, then the conjugate is that your imaginary part has negative sign. Then the fundamental solution has different form, which is e to the alpha x times cosine beta x. I saw many of students in the test or in the quiz forget to put the x on the exponent. So be careful that there is an x on the exponent of e and x on the cosine sign. So x are on the both side. So this is called, these are the fundamental set of solutions. Well, this is a side note. And let me explain. I'm sorry, so I forgot to put this in the bigger picture, so sorry. So this is a characteristic polynomial, and this is the theorem. Okay. Now, let me explain why that makes sense. So I have to go to the blackboard. So since I put the slide in a small figure, is there any questions on theorem or definition? Please ask right now before I go to the blackboard. No questions? Okay, let me explain why we need a characteristic equation to solve this differential equation. So the idea is simple. You have a differential equation, alpha 2y double prime plus alpha 1 y prime alpha 0 y equals to 0. So what this equation tells you is that if y is a solution to this differential equation, it tells you that y and y prime and y double prime, the set of all three functions, these are all different functions, are linearly dependent. The set of three functions is linearly dependent, not independent. Okay? So if you recall the definition of linear independency from the week 5, I guess, it simply says that it is linearly dependent if there is non-zero constants whose linear combination becomes identically zero. So this equation says any solution satisfies that y prime, y double prime is linearly dependent. This is simply the definition of linear dependency. And when I say intuitive idea of linear dependency, any two functions are linearly dependent if the shape of graph is nothing but constant multiple of each other. If you have three functions linearly dependent, then you also can generalize intuitive idea of linear dependency between two functions such that three functions, the shape of the graph of three functions are basically a multiple of each other plus minus or sum of the constant multiple of other functions. So basically, I can say that this means y1, y prime, y double prime. So this is intuitively, not rigorously, are basically the same functions. So same means it doesn't mean that it's actually the same function. It basically are similar functions. But if you're looking at the polynomial, such as y equals to x squared, then the y prime is 2x, and y double prime is 2. And these three functions, x squared, 2x, and 2, are all different functions. They are not linearly dependent. They are linearly independent. Or if you're looking at the function y1 equals to e to the x and y2 equals to e to the 2x, these are also linearly independent. And also, if you start from sine x and you take the y prime, which is cosine x, these are also linearly independent. Sine and cosine are linearly independent because they are not multiple of each other. They are shifted but not multiple. So there are a few cases when you take a derivative that the result is linearly dependent function, basically the same function. That's the exponential function. If you take the differential of an exponential function, you have a constant coming out from the exponent, but basic shape does not change. So omni case when y prime, y double prime are linearly dependent, meaning that these three functions are basically the same function, is when y is equals to some lambda x with constant lambda. Okay. In that case, the three functions y double prime are linearly dependent. So when I plug in y equals to e to the lambda x to the differential equation, I get alpha 2 lambda squared, because each time I take a derivative, I get lambda coming out of this exponential. So when I take a second derivative, I get lambda squared, e to the lambda x, alpha 1 lambda, e to the lambda x, alpha 0, e to the lambda x. That must be equals to 0. So let's take e to the lambda x together. And the coefficient becomes alpha 2 lambda squared, alpha 1 lambda, and alpha 0 equals to 0. Now that must be identically 0 regardless of what x value is. So this coefficient must be always 0. So in order to have e to the lambda x be a solution to this differential equation, you need your lambda satisfy this equation, quadratic equation. That's the characteristic polynomial. Now, so that tells you the first part of the theorem. So if you have two solutions, then, so if you have two real roots, then you can have two possible functions as your fundamental solution. And if you have same function, same lambda, which means that you have a double roots here, you can simply use reduction of order to find the second root. So we mark is that if the characteristic equation has a double root, say lambda, then use the reduction of order to y1, which is e to the lambda x. So we know that e to the lambda x is one of the solutions. By looking at the characteristic polynomial, we have no idea what's the next solution. So we just use the reduction of order. So it says y2 is given by y1 times the integral of y1 squared, which is e to the 2 lambda x, and e to the negative of pxx. But now, when I use the reduction of order, I need 1 on the coefficient of y double prime. And I'm assuming that this coefficient alpha 2 is not 0, because if it's 0, then simply it's a first order derivative differential equation. And that's not the case we're talking about. We're only talking about the second order derivative, a second order differential equation. So I can I can divide alpha 2 on both sides. So I get y double prime plus alpha 1, alpha 2, y prime, alpha 0, alpha 2, y equals to 0. So this is our p, alpha 1 over alpha 2. So this is alpha 1 over alpha 2 dx dx. And this is simple because e to the lambda x times now e to the minus alpha 1 alpha 2 plus 2 lambda x. Let's combine the exponent here. So we have minus alpha 1 over alpha 2, and we have minus 2 alpha if I put this guy into the numerator. So this is our exponent. And if I take a derivative, let me erase this. We have e to the lambda x times of what? Minus alpha 1 alpha 2 plus 2 lambda over 1 over this, and e to the minus alpha 1 alpha 2 plus 2 lambda x. So this is minus 1 over alpha 1 alpha 2 plus 2 lambda times e to the here we have plus lambda minus 2 lambda, so minus alpha 1 alpha 2 plus lambda. Sorry, so this is, oh, I'm sorry. So before I actually do this, I have to check that this is actually 0, because I cannot take an integral of 0 denominator. So let's look at this exponent here. Okay, we have lambda as a double root, so which means that this characteristic equation, lambda squared plus alpha 1, alpha 2, lambda plus alpha 0, alpha 2, is basically, well, let me just give a different notation here. Say lambda 0, just to differentiate our variable lambda and the root lambda. So root lambda, lambda 0, and lambda 0, lambda 0, lambda 0, lambda 0. So basically it says that this has a double root lambda 0, so it can be written as a perfect form, lambda minus lambda 0 square. So if I rewrite this is lambda squared minus 2 lambda 0 lambda plus lambda 0. So what it says is that these are identical equations. So alpha 1 over alpha 2 is minus 2 lambda 0. So alpha 1, alpha 2 is minus 2 lambda 0, meaning that alpha 1, alpha 2 plus 2 lambda 0 equals to 0. So that tells you that this part is 0. So this is e to the 0, which is 1. So this is integral of 1. So therefore, we get x. When I take the integral of 1, it's x times e to the lambda 0x. That's the second root. Okay? So that explains the second of the theorem. And the third part of the theorem tells you when you have a complex root, then we have weird formula, not the exponential. We have cosine and sine appears. And that's not weird because we learned the Euler formula I think in the first week, right? So in the first week, we learned about the Euler formula, which says that e to the x plus iy is e to the x cosine y plus I times e to the x sine y. This is the Euler formula. So it seems weird that you have a complex on the exponent of e, but this is, you can take as a definition, or you can derive this formula using Taylor series later in our second semester. And the result is also a complex number which has a real part as e to the x cosine y and imaginary part e to the x sine y. So suppose that you have lambda equals to alpha plus minus I beta as your root. And now what happens to e to the lambda x when I take a derivative? So e to the lambda x, which is e to the alpha plus minus I beta x, is ddx of, if I use this formula, what happens is, this is, well, let me write again. So e to the alpha x plus minus I beta x. So this is ddx of e to the alpha x. And then we have an imaginary part becomes the constant y part multiplied to the I becomes the inside of cosine and sine. So this is cosine beta x. So if you have a plus here, then this is formula. If you have a minus, this has the same effect when you have a y replaced with minus y. So let's say we have minus y. What happens is if you just plug in minus y in here, you get same cosine y because cosine is an even function. The value of cosine is same if you take the negative inside or not. So you have e to the x cosine y. And sine is an odd function. You have a negative sign comes out. So you have a minus I e to the x sine y. So that's the effect of when you have a negative on the imaginary part. So you have a negative or positive in the imaginary part. So you have a positive, you have positive. You have a negative, you have negative. So you have a plus minus sign appears in here. So e to the alpha x sine beta x. So that's a derivative. That's the derivative. And now we can take a derivative of complex number because the imaginary part and real part and imaginary part, I'm so sorry, I forgot to put I here, also contains the function of x. Okay, so you just take the derivative in terms of x. So here you get e, so take a derivative on each part, e to the alpha x cosine beta x plus minus I ddx of e to the alpha x sine beta x. So this guy is alpha e alpha cosine beta x plus beta e alpha x sine beta x, and sine becomes negative. And then plus minus I of alpha e alpha x sine beta x, and plus beta e alpha x cosine beta x. Okay. Let's combine terms here. First of all, let's combine cosine here. So we have alpha times, so I'm going to combine cosine beta x. So here beta is multiplied with plus minus I, so it's plus minus IB times e to the alpha x cosine beta x. And now, how about sine? So we have sine comes from, well, let's just put the minus beta plus minus I alpha e to the alpha x sine beta x. Okay. So, and then let's look at this complex number carefully. So I want to take the I in front of this multiple. So you have, if you take an I outside, then where we are. So we have alpha here. If you take plus minus alpha, and then in order to get the minus beta, you need to multiply minus, so actually plus alpha, plus I beta, right? Plus, well, let me put that in this way. So it's a little bit getting awkward, but that's required so that I can express what I want to say. So let's put the plus minus sign in front of first. Okay, so then minus beta appears when I take a negative plus instead of plus minus. Instead of plus minus, I put the minus plus in front of the beta so that it always becomes negative 1. So here I get just I alpha here. Okay, and also take the I outside of this parenthesis. We get plus minus I times now alpha, and then this minus plus beta is nothing but, let me write in here. So e to the, minus plus, I'm sorry, I, minus plus beta can be written as, here we have plus minus I beta. Because if I take a plus inside the parenthesis, I times I becomes negative, so I get the negative side negative. And then if I take a negative in the parenthesis, I get I as a negative and then minus multiplied so that I get the plus. So negative plus beta is same as this guy. So if I take the I out of this negative plus beta, then I get plus minus I beta. Okay. So the result is that alpha plus minus I beta e to the alpha x cosine beta x. And then here I also can write as plus minus I of alpha plus minus I beta e to the alpha x sine beta x. And then let's combine this alpha plus minus I beta. We get alpha plus minus I beta, and then e to the alpha x cosine beta x plus minus I times, so here's I times e to the alpha x sine beta x. And what was this guy? So this guy is nothing but e to the alpha x plus minus beta x. And if you combine the exponent coefficient of x, this is simply e to the lambda x. Alpha plus minus I beta e to the lambda x. So here we have plus minus always consistent with the plus minus chosen in here. If I take a plus here, everything is plus, and if I take the negative here, everything is negative, because that's how I choose this order of sign, plus minus sign. So, and then final result is that this is lambda times e to the lambda x. So what's the result? We start from the derivative of exponential with complex coefficient. The result is a complex number which has lambda times e to the lambda x. So if lambda is complex, the derivative of e to the lambda x is same as lambda times e to the lambda x, the same formula that you have in real case. So the formula holds whenever you have a complex number. So therefore, this is the reason why we have the third part of the theorem, because you can simply take your fundamental solution as the exponential function with a complex coefficient. So let's say lambda 1 is alpha 1 plus beta 1 I beta 1, and lambda 2 is just alpha. Let's drop the index here. Lambda 2 is alpha minus I beta. Okay. Then y1, which is e to the lambda 1x, which is e to the alpha plus I beta x, and y2, which is e to the lambda 2x, which is e to the alpha minus I beta x. These are fundamental solution. But however, if you write your solution C1 y1, C2 y2, that seems like it's a complex function, because you see C1, now y1 is e to the alpha x cosine beta x plus I e to the alpha x sine beta x. And here C2 times e to the alpha x cosine beta x minus e to the alpha x sine beta x. This is the solution. This is the general solution. And it seems like we have an I in the formula, so it seems like it's a complex number. However, it's not a complex number if you plug in the real initial conditions, because you can rearrange these functions so that C1 plus C2 is our constant coefficient of e to the alpha x cosine beta x, and here we have I C1 minus I C2 times e to the alpha x sine beta x. And let's just replace this guy into D1 and this guy into D2. Then I can rewrite my solution, complementary solution, strictly in terms of real functions. e to the alpha x cosine beta x, and d2 times e to the alpha x sine beta x. So you have a complementary solution expressed in terms of real solution. There's no I in here. Although the I, you might think that I is hidden in the formula of D1, D2, but when you actually compute your particular solution using the initial value condition, D1, D2 becomes real numbers. So what we really have is C1, C2 are complex number, not D1, D2. Okay? So C1, if you plug in your initial value condition in here, in the original formula, you will get a complex number on C1, C2, but if you can replace, rewrite your solution in terms of real value function, your constant coefficient becomes the real number again. So you can just start from this formula without considering the complex numbers in the beginning. However, the idea why we have this as a fundamental set of solution is because of the Euler formula. Okay? And sometimes it's easy to just consider, start with this complex formulation when you want to compute something, but that's beyond our material, so we're not going to talk about that here. So that's the third reason, the reason for the third part of the theorem. Okay. If you have any question, let me know. No question? Okay. Well, this is a little bit of generalization, but we said that we're only going to talk about the second order derivative, so let's skip the remark. So example, it's really easy if you want to just apply your apply the theorem. It's really easy. So we're not going to do the second example because that's the remark part. The characteristic polynomial can be generalized to higher order linear differential equation if the coefficients are all constants. If you have three roots, then you have three fundamental solutions. So in all other cases, well, I think we can just understand the remark by looking at the example. So let's do the example, both examples. If you have any question, please ask. I think I should go faster than this, but I'm trying to be as concrete as possible. So you can stop me anytime if you are not understand anything. So this is first example that 2y prime double prime minus 3y prime plus 4y equals to 0. So characteristic polynomial is finding a complementary solution to the homogeneous differential equation. So you don't have a non-zero term in the right hand side. So characteristic polynomial is 2 lambda squared minus 3 lambda plus 4, and you have to find the roots. And you take the root plus minus 9 minus 2 times 4, which is 3 plus minus 1, which is 2 and 4. Well, you can just using the factoring of second order, factoring the quadratic equation. And the complementary solution is C1 times e to the 2x and C2 times e to the 4x. Okay. Let's look at the second example. So second example is not a second order differential equation. It's a third order differential equation. The last y is 0 because of coefficient is 0. You can find the characteristic equation in the same way that you have the characteristic equation in the second order differential equation. You have this differential equation. The third order derivative becomes lambda cube, and the rest is similar. So 4 lambda squared minus 5 lambda. Now y, if there is a y, then you have a constant, but there's no y. So this is it. So we have to find the root satisfying this cubic equation. So take lambda out, and lambda squared minus 4 lambda minus 5, and that's lambda times lambda minus 5 lambda plus 1 equals 0. So you have 3 distinct roots. So therefore, the complementary solution is the linear combination of 3 fundamental solutions. One is when lambda is 0, C1 times, so root are 0, 5, and minus 1. 0 is 0 times x, which is just constant, okay? And C2 times e to the 5x, and C3 times e to the minus x. So simplify this part, C1 plus C2 times e to the 5x plus C3 times e to the minus x is the complementary solution. So characteristic equation method is generalized to higher order differential equation, and that's the only case that we can have a generalization. Okay, so let's look at the slide again. So Cauchy-Euler equation. This is a slightly different type of differential equation because you have x squared and x on these terms. Lambda. Is it wrong? Lambda. Did I compute wrong here? So, I forgot 2 over here. 2, 3 square minus, right? I forgot 2 here. 1 and 2, right? Let's just check. So you have 1, 2, 3 plus minus b square. I think, okay. I forgot. Okay, so I think I used wrong formula here. So I just want to use the formula of, okay, so it's 2 times 2 of 3 plus minus 9 minus 4 times of 2 times 4. Yeah, I made a mistake, sorry. So it's 3 plus minus of 9 minus what? 32. 32 minus 9, 32, 23, I. Right? This is right. So, what do we have here? C1 e to the 3x over 4 cosine square root of 23, right? 32, yes, over 4x plus c to e to the 3x over 4 sine square root of 23 over 4x. 2a, b, right? 맞죠? 이거는. 이거 시험 내면 항상 이거 해공식 틀려가지고 틀리는 친구들 많아가지고 맨날 나도 이거 조심하라고 했는데 나도 틀렸네요. 맞죠? 아무도 맞다고 말 못해. 네. Okay, thanks for correction. Okay, so how far we have to go? Okay, let's finish with the Cauchy-Euler equation. I think you get. Okay, well, it's sometimes called Euler equation, sometimes called Cauchy-Euler equation. So the Cauchy-Euler equation is of this form, and the characteristic equation of Cauchy-Euler equation is slightly different. Instead of putting lambda square, you put lambda minus 1, okay, for the second order derivative. And first order derivative, we have lambda. So you have always the one negative multiple of the lambda, okay? So if you have two roots of characteristic polynomial, then the fundamental solutions are x to the lambda 1 and x to the lambda 2. Instead of exponential, you have x to the lambda. So power functions are the fundamental solution to the differential equation. If you have a double root, then x lambda is one root and ln log x times x lambda is another root. And if you have complex roots, then these are the fundamental solutions. Let me explain, and then the rest of the questions are not hard. So let me explain why we have such formula. So at the end, if you memorize the formula, then you will forget. I'm pretty sure, I'm 100% sure that you will forget everything. But if you understand why you have that formula, even though you will forget the formula, you can reproduce the formula. So the reason why we have x lambda as a solution, type of solution of differential equation is that if you take a derivative of x lambda, you get lambda x to the lambda minus 1, right? And also, if you take a second derivative of x lambda, then you get lambda minus 1, x to the lambda minus 2. So if you have y equals to x to the lambda, then y and y prime, which are x times y prime, which is lambda. Well, you have x to the lambda minus 1 for y prime, but you have a multiple of x again, so you get x lambda. And x squared y double prime, because lambda minus 1, x to the lambda. So these three functions are linearly dependent, right? So this is the form of the solution satisfying differential equation, because the differential equation basically says that you want to find y satisfying this equation, and it says that this function and this function, all three functions are linearly dependent. So we have x lambda as a candidate for the solution. Now, once we've, sorry. 네, 미안합니다. 바로바로 얘기해 주세요. 제가 까먹으니까. Okay, so here we have the formula. And now suppose that we have, well, so the first part is not hard. We have two distinct root, x lambda 1 and x lambda 2. These are linearly independent. If lambda 1 and lambda 2 are different and these are real numbers. And for the second case, we use the reduction of order because we know that lambda 0 is one root and second root is same as lambda 0. So we take the reduction of order, which is x to the 2 lambda 0 e to the negative of px dx and dx. That's the second root. But what's the px? So these are our equation, and if I rewrite this using the coefficient y double prime equals to 1, then this becomes y double prime plus alpha 2 x alpha 1 y prime alpha 2 x square alpha 0 y equals to 0. So this is x, this is px, okay? So if I plug in that one, we have x to the 2 lambda 0 e to the minus of alpha 2x alpha 1 dx and dx. And keep compute. We have x 2 lambda 0. Here we have e to the minus alpha 1 alpha 2 ln x dx. And you see this coefficient becomes the exponent of x inside of log, and e and log cancels out. So we have x lambda 0 of x to the minus alpha 1 alpha 2, and then let's put the 2 lambda 0 dx. And this becomes 0 because if I put parentheses here, since lambda 0 is a root to let's check out why this becomes 0. So this was alpha 2 lambda minus 1 plus alpha 1 lambda alpha 0 equals to 0. Alpha 2 lambda minus alpha 1 minus alpha 2 lambda plus alpha 0 equals to 0, right? So if I take alpha square plus alpha 2 alpha 1 minus alpha 2 times lambda plus alpha 2 alpha 0 equals to 0. Since lambda 0 is a double root, this is simply lambda minus lambda 0 square equals to 0. So this equation is exactly the same as lambda minus lambda 0 square. So if you compare the coefficient of lambda, a little bit weird. Let me modify later. So this is equals to minus 2 lambda 0. So with this one, we have px. We have px minus of px 2 lambda. Oh, okay, nothing wrong here. So okay, this is not 0. It survives. So we have lambda 2, lambda 1 plus 2 lambda 0 equals to alpha 2. Okay. Not alpha 2, I'm sorry. So alpha 2 over alpha 2. So it's 1. Okay. So this is 1 inside the parenthesis. So we have x to the lambda 0 integral of e to the x to the negative 1 dx. So it's basically 1 over x. So when you take the integral of 1 over x, it's ln x. So x lambda 0 ln x. So that's the second root. That's how we get the second part of the theorem. And for the third part, it might seem weird, but it simply it follows from the definition. So here we have x to the alpha plus minus I beta. Okay. So by the rule of exponent, we have so times x. Okay. I'm sorry, it's not times x. So just x. We have. I'm confused with the exponent. So we have x to the alpha times x to the plus minus I beta. So this is okay. This is a real valued function. But this part I want to express in terms of real valued function. Let's consider x to the I beta. Okay. Now, not only for this purely imaginary number, when I have x to the lambda, this is always defined as e to the lambda log x. So this is the definition. When you take x to the square root, you're not taking a square root number of times of x. So only time that you can define your power function with a product is when you have an integer power of x. When you have a real number as a power of x, then you always define it as the composition of exponential function and log function. And this matches with your property that you know. So I just plug in this I beta inside of lambda here. We have e to the I beta ln x. Now we have Euler formula, which is, this becomes cosine. So the imaginary part, beta ln x, is inside. And here we have I sine beta log x. Okay. So if I have plus minus sign, I have a plus minus sign here. So this part is now becomes x to the alpha of cosine beta ln x plus minus I sine beta ln x. So in principle, you have two fundamental solutions. One is x to the alpha plus I beta, which is x to the alpha cosine beta ln x plus I x to the alpha sine beta ln x, and this is y1 and this is y2, which is alpha minus I beta and x alpha cosine beta ln x minus I x alpha sine beta ln x. However, as I mentioned, when you express your complementary solution C1y1, C2y2, you can rearrange your coefficient so that only the real function survives. So you can express as d times of x alpha cosine beta ln x plus the 2 times x alpha sine beta ln x. So you can take these two functions as fundamental solution. So x alpha cosine beta ln x and x alpha sine beta ln x are fundamental setup solution. Okay. So if you, applying the formula, applying this theorem is not hard at all. Just don't make a mistake on finding the roots, as I did in the previous example. Just don't make a mistake on computation. Okay, so the rest of the material will be covered in next lecture. So if you have any question, please ask before we start the MATLAB. 질문 있어요? 이번에 숙제하실 때는 매틀랩 쓰셔도 돼요. 그러니까 계산이 복잡하면 매틀랩으로 했다. 근데 매틀랩으로 하면 커맨드를 같이 첨부를 하셔야 돼요. 뭐 화면 캡처하시든지 커맨드 라인을 같이 이제 타이핑을 해서 보여주시든지. 자, 질문 없으면은 매틀랩 좀 해봅시다. 다음 주 금요일까지. 이번 숙제는 다음 주 금요일까지요. 2주 있어요. 2주. 자, 일단은 first, let me show how to use MATLAB when we solve our differential equation. So, easy part. Okay. So, for example, if you want to find the root, so let's say finding roots. Well, for example, x squared minus x plus 1 equals 0. There are two ways of finding roots. One is you can symbolically find the exact root, or you can find numerically the approximate root. So if you want to find the exact root, then you have to use the symbolic toolbox. So first method is finding an exact root. Is first take the x variable as symbolic variable and solve x squared minus x plus 1. So it then gives you the answer. So this is very simple. Because you have a symbolic toolbox, you can use this method, solve command, only for the symbolic variable, and it gives the two roots. One is 1/2 minus of this imaginary part, okay, and the other is, so it's a plus imaginary part, okay. I think it becomes simple if you use simplify command here. simplify. Well, it doesn't get simpler than this. So anyway, you can, in this example, you can easily find root by your hand, but if you want to verify your answer is correct, then you can easily check. Or let me verify what I computed last time is right. So in the example of here, which one is our example? Yeah, this one. So I had a root, but I'm not sure whether I did right. Then just plug into the MATLAB, 2 minus 3 plus 4. Okay. So for example, 2x minus 3, here, minus 3x plus 4 goes to 0. Then I can simply solve 2 times x squared minus 3 times x plus 4. Run. Okay. Okay, let's just, there's a error in the command here, so just let me, okay, so this is our result. Yeah, that my calculation is correct. 3/4 plus minus square root of 23/4 times the imaginary part I. Okay, so you can use this solve method. And also I want to tell you how to plot the implicit function. So suppose that you have this implicit equation, exponential minus xy. So y is a function of x, but you cannot express y explicitly in terms of x. This is implicit equation explaining the implicit function y. If you want to plot the function, then implicit function, then you can use f implicit command, and what comes next is the anonymous function having two variables inside. So you have x and y defined as a independent variable, and what you are actually plotting is the graph of fxy, which is y minus xy, when this becomes 0. So basically, if you have a two-variable function, the graph of two-variable function is the surface inside of three-dimensional space. But I want the graph of implicit function. So the one way I can do that is plot the section of a graph of two-variable function when the value of two-variable function is 0. So this is what I want, okay? But I'm using this function, okay? I'm using two-variable function to plot the graph of my implicit function because that's the surface of this two-variable function intersecting when the value of function equals 0 is exactly the graph of implicit function. Okay, so that's one way you can do that. And well, let's say I have a graph, and suppose that this implicit function is the solution to this differential equation. I think you can do this, find the solution using the integrating factor. And this solution is a solution to the initial value condition y0 equals to 1. So we found a particular solution satisfying this condition, but suppose that I want to find an approximate value of y1. So approximate value of y when x equals to 1. So that means I need to find y satisfying y equals to x of minus y, right? So you can guess that this is equals to the point y coordinate of the point where the straight line and exponential graph intersect each other, or there are other methods to find this, but one way you can find this is this way. So you can use f0 y minus x minus y. So basically, if you want to find this value, then you can set your function fy equals to y minus x minus y, and what you're trying to get is the root of this function f, because that's when y becomes exactly equals to exponential of minus y. So f0 is the command that finds the root of given function. So I want when this y minus x of minus y becomes 0. So result, I'm sorry. So So f0 also requires initial point. So let's say, like in Newton's method, so this f0 approximately finds the root, but there could be many roots. So it doesn't find all roots of this function. It finds a single root next to the initial point. So if I suppose that I start with y equals to 0, if 0 is the root, then it's fine. But if it's not, then it tries to find the closest root to the 0. You can change this 0 to the other value, but if it will spit the root next to the initial value. Okay, so if I put 0 here, then it finds the root nearest root to the 0. If I put 1, probably it will have the same root, because I think there is only one root here. But anyway, you have to put the initial point here. So this is important. So this is a numerical way of finding root, and I don't think there is an exact solution to this equation. So symbolic method cannot be used here. And well, the other part is for the next lecture, when we are required to find constants a, b satisfying this equation. We will do this in next time. So I think when you're doing the homework, you have to be able to find the numerical solution to the differential equation, second order differential equation that we done in the last week, and also you have to be able to find a approximate value of the solution at the point at the random point. Okay. So if you're not comfortable with using the MATLAB yet, please let me know at the end of the class. I can do this again. So time is almost over, so we will finish here and have a nice lunch and see you next time.